Okay, now let us talk about the third part of the chapter, which is the power dissipation in a resistor and the mean square current. Let's first talk about what a pure resistor is. It converts electrical energy purely into heat energy, right? So your heater that heats water, right? And as a pure resistor looks like this, right? Or even those that you use in the labs, right? Those are your pure resistors. If you think about how power dissipation works in a DC, right? It is a reminder of what you have learned in secondary school. You see that when a current passes through, right, it converts it into heat, and the power given is P equals to I squared R or V squared over R. Okay, and usually we assume a constant current, constant DC. Okay, but for AC it's very different. Look, when the current is small, the power dissipated is small. Current is larger, power dissipated is larger. When it's largest, to the right is the power dissipated is the largest, right? And then it comes back down, and then when it goes to 0, and then it switches direction. Okay, so we realize that the direction of current is actually not important for the calculation of power dissipation, right? The power dissipated at any instance in time depends on the current value at that instant. So how then, right, should we calculate the power of an AC, right? So that brings us to the next slide, that we shouldn't okay, sorry. So here is about the instantaneous power dissipated first. Okay, so as I was saying, right, as the current changes, the power dissipated changes, and the instantaneous power is generated by this. Okay, however, uh, if we want to find the power of a heater, the instantaneous power at any point in time is not really what we are concerned with. We are generally concerned with the average power. Okay, so for average power, right, we realize, okay, that the power equals to I squared R, right? And we can, because R is constant, we can take it out of the brackets. Okay, and same thing here, if you use P equals V squared over R, because R is constant, we can take it out of the brackets. And here we realize that the average power dissipated in a resistor is the mean square current times R, or the mean square voltage divided by R. Okay, so note here that I said mean square current, and this is the mean square current. It is not the same as the square of the mean current. Okay, so the mean square current is the mean of the square current. I just need to say this again. The mean square current is the mean of the squared current over one period of interval. Okay, so you will take the square first, then you will mean. Okay, whereas the square of the mean current is the mean current first, then you square. Why is this very important? Because if you write mean square current times R, you get a power that's non-zero. However, if you write the square of the mean current times R, you should get 0, because for alternating sinusoidal current, the mean current is 0 because it's equal portions above 0 and it's equal portions below 0, and you take the average, it becomes 0. Okay, right, so this part, the main aim is to differentiate for you, to introduce to you firstly what is mean square current as well as mean square voltage, right, in your notes, and to ensure that you do not write mean square current as the square of the mean current, right? So this is something to take note of.